My name is Carol Burns, and I'm the Deputy Laboratory Director for Research at Lawrence Berkeley Lab. On behalf of Director Witherall and the entire Berkeley family, thank you so much for being here. We're so excited to celebrate this event. So I think we have one slide for the safety briefing, which is to say, in the event of an emergency, there are, first note, the emergency exits. Follow a Berkeley Lab employee. We'll go to the H1 parking lot as the muster area, so just follow somebody who knows where they're going. We also, which is about the best thing that's what I'm doing in this job after a year, is I'm following somebody who knows what they're doing. All right, well, let me go ahead and just give you a general welcome. Good morning, everybody. Welcome to all of our attendees, both in person and in Zoom land. We have a number of important guests here today we'll welcome over the course of the morning. We want to acknowledge celebrating such a significant event, which is the launch of ESnet's sixth generation of DOE's advanced network that is dedicated to serve our community for the next decade to come. We want to also celebrate ESnet's 35 plus years of service to the DOE science mission, as well as the innovations in networking it's provided that support research and contribute to the internet at large. These contributions began well before the internet was commercialized as it is today. During these 3+ decades, ESnet has become a trusted resource to our partners in DOE, congressional stakeholders, and to the global scientific community. And our speakers today are going to reflect these themes. I also want to take a moment today to acknowledge the community leaders that are joining us in person. Berkeley City Council members Rigel Robinson and Terry Taplin, along with representatives from the offices of Senator Alex Padilla, Speaker Nancy Pelosi, Congresswoman Anna Eshoo, State Senator Nancy Skinner, Alameda County Supervisor Keith Carson, and Berkeley Council member Susan Wengraf. So thank you all for being here. Also joining us from the University of California Office of the President is Dr. Teresa Maldonado, Vice President for Research and Innovation. At Berkeley Lab, our collective mission is to bring science solutions to the world. As leaders and citizens of the laboratory, we are entrusted to care for people, research, and resources that make our mission possible, a responsibility we call stewardship. ESnet is a stellar example of how we're able to demonstrate stewardship, not just at our laboratory, but across the entire DOE research complex. Some of you may not know that ESnet is actually one of DOE's 28 user facilities. For those who are not familiar with user facilities, these are DOE sites hosting the most advanced science tools serving all DOE-funded research domains. These include supercomputers, light sources and neutron sources, accelerator test beds, as well as facilities for studying the nano world, the environment, and the atmosphere. Here at Berkeley Lab, we're very fortunate to be home to 5 of these scientific user facilities, including ESnet. In this role, ESnet operates as the central circulatory system connecting all of our national labs and DOE's nationwide facilities, rapidly moving data between these sites so that scientists can reach instruments, computers, experiments, and people around the world seamlessly, no matter where they are. It is also a critical capability in democratizing access to these tools. Ernest Orlando Lawrence was a trailblazer in promoting the concepts of team science and big science. Even 85+ years later, this legacy continues to make up the basic fabric of Berkeley Lab culture. It is through interdisciplinary team-based science that we can produce innovative solutions for the complex problems that we face. ESnet and its new network, ESnet6, extends this philosophy globally. The network makes it possible to bring together worldwide teams serving big science problems. Berkeley Lab scientists are leading global science collaborations to develop breakthrough science instruments that hold the promise of unraveling some of life's greatest mysteries, as well as solving some of the world's grandest challenges. ESnet has built direct partnerships with collaborations that require the capabilities of ESnet6 with the intent of creating a replicable model for projects across all of DOE. For example, in the area of high energy physics, the Dark Energy Spectroscopic Instrument, or DESI, will utilize the expanded capability and speed of ESnet6 that is required to rapidly distribute very large observational data sets to computing resources and collaborators worldwide. This capability is going to be very important In the first year of the survey, more than 18 million galaxy redshifts were observed, more than all previous redshift surveys combined. That's the scale of the data problem that we're facing. For the new gamma ray energy tracking array instrument at FRIB, the Facility for Rare Isotope Beams, supporting our nuclear physics community, ESnet has worked with the project from the beginning to integrate networking and computing to the instruments designed to ensure researchers can access and move data from this major DOE experimental facility. There are many more examples, and you're going to hear some more, pardon me, from technical speakers this morning, later in the program, from Berkeley scientists David McCallan and Almgren. Both use exascale computing capabilities to help us understand and predict the impacts of catastrophic events like earthquakes and how we can help address climate change through the development of wind energy technology. In all of these cases, ESnet has been embedded in the collaborations from the start to ensure the networking can help improve science outcomes. I can't wait to see what comes next. It is now my distinct honor to welcome and introduce someone quite familiar to the Berkeley Lab community, Congresswoman Barbara Lee. Congresswoman Lee has represented California's 13th congressional district since 1998. She is the highest ranking African-American woman in House leadership and also a senior member of the influential budget and appropriations committees. Throughout the Congresswoman's career, she has been a true champion for diversity, equity, and inclusion, workforce development, research, and innovation, all areas central to the lab's mission. Congresswoman Lee, many thanks for your leadership in these critical areas and so many others that are important to the interest of our district and to the nation as a whole. Today, as we gather to celebrate the launch of ESnet and its role in increasing ESnet6 and its role in increasing the connectivity of DOE-supported research, we're thrilled to have remarks from our representative to the United States Congress. Please join me in welcoming the Honorable Barbara Lee.
Well, good morning, everyone. It's really great to be home. Every time I come to the lab, I think I'm coming to the future, but today I feel like the future is here. So thank you so much. And thank you, Carol, for that very kind introduction. And I'm so happy to join this unveiling ceremony for ESnet6. And I want to congratulate the lab on this really major accomplishment, and also to Director Brown, Department of Energy, to Mr. Monga, and for your amazing work. I just want to thank all of our elected officials, everyone who has really pulled together to bring this to fruition. And let me just say how proud I am of the mission and goals of ESnet program. It's advanced the DOE mission by linking the funded scientists and the pathway that connects instruments, people, computational resources, and data around the globe, regardless of the location. Through my work on the House Appropriations Committee and the Budget Committee, you know, I constantly work so hard to make certain that our limited resources are used effectively to create an equitable and sustainable future. Scientific research, including our own ability to exchange information and ideas, is key to that future. And so I think it's remarkable that every day ESnet is carrying data. This is really mind-boggling, from tens of thousands of researchers from national labs, universities, and industry. And these interactions are contributing to a safer and healthier world for future generations. And also I'm impressed that ESnet has even contributed to our response to the COVID-19 pandemic by providing scientists with access to DOE supercomputers to enable relative research. So again, I want to thank everyone, especially the Department of Energy and the lab, for these investments. ESnet is truly the next step. It's a timely response to significant growth in scientific data. This research is integral to our ability to move towards a more just and equitable world. The House Appropriations Committee has provided support for ESnet over the course of 6 fiscal years. And believe you me, given the constraints that the committee faces and the priorities, I'm really pleased to see the project completed on time and ahead, quite frankly, of schedule. So you know I'm going to be very vocal in letting my colleagues know this as we move into this next cycle. So thank you so much for making me proud. Once again, congratulations to the Berkeley Lab and to the success of ESnet and the ESnet 6 project. It's really my honor to be an advocate for our community each and every day. And your work is not only a part of our community, though, and my congressional district, but a part of the nation's response on clean energy and climate goals. So thank you all again very much. Really wonderful to see everyone. And again, I just have to salute you for making my district and myself very proud. And I can't wait to share what we have done here with my colleagues. Thank you again.
We're going to have a very interactive. We're going to have some people virtual, some people live. So it's going to be an interesting morning. And I'm now very pleased to introduce a video we received from US Senator Alex Padilla. Senator Padilla's career in public service spans more than 2 decades at the local, state, and federal levels. For 6 years while in the state Senate, he served as chair of the Committee on Energy, Utilities, and Communications, where he was instrumental in developing California's renewable energy and climate policies, among the most ambitious in the world, as well as expanding access to broadband and modernizing California's electrical grid. Now in the US Senate, he serves on several important committees, including Budget, Environment and Public Works, Homeland Security, and Governmental Affairs, Judiciary, and Rules. Senator Padilla was unable to join us today, but wanted to convey his thoughts on this occasion. So we have a video from him.
Hi, I'm Senator Alex Padilla, and it's an honor to join the Berkeley Lab and everyone celebrating the unveiling of ESnet6 today. Now, as a mechanical engineer by training, I know just how important it is to connect researchers with the instruments, people, and resources they need, regardless of location. And that's why ESnet6 is so critical, and why I know you are so excited about what the future holds for our nation's researchers. Now, in the Senate, I'm proud to have supported federal funding for our national labs that help complete the ESnet6 project. I know projects like this will lead to innovations and breakthroughs in clean energy and climate. Congratulations again. I can't wait to see what's in store.
All right, we're switching to another mode. Now we're going to have a live virtual presentation. So we're really excited to virtually host remarks from Dr. Asmeret Berhe, Director of DOE's Office of Science. Prior to this role, Dr. Berhe was a professor of soil biogeochemistry, the Ted and Jan Velasco Chair in Earth Sciences and Geology, and interim associate dean for graduate education at the University of California, Merced, and once a graduate student at Berkeley Lab. As a soil scientist, her research focused on how physical processes such as erosion, fire, and changes in climate affect essential elements in the Earth system. She has received many accolades for her efforts to ensure equity and inclusion of people from all walks of life in the research community. Please join me in welcoming Dr. Berhe.
Thank you, Carol. Good morning, everyone. Good morning, Congressman Lee and others at LBL leadership and everyone in attendance today. It is an incredible honor for me to join you all today to celebrate the unveiling of ESnet6. I want to congratulate and recognize the staff from ESnet, the Lawrence Berkeley National Lab, all the industry partners, and the U.S. Department of Energy Office of Science for their successful collaboration to deliver these major accomplishments. As you know, collaboration and big team science is really at the core of everything that we do at the Office of Science and across the national lab systems. And since its inception, ESnet has been the literal backbone for how we collaborate across vast distances and between our world-class user facilities. I know this personally. I value how important these collaborations are for enabling our science and broadening access to our incredible capabilities to a vast, broader public that we are honored to serve. User facilities, as you heard from Carol's talk earlier, are these wonderful mediums through which we provide the opportunity to researchers to collaborate with world-class scientists, and that's in fact my connection with the National Lab and how it started at Berkeley, because I've had the opportunity to work at the lab as a graduate student and collaborate with folks. My entire career really focused at the national labs and the advanced scientific facilities that are managed by the Office of Science. And from the time I was a PhD student at the University of California, Berkeley, my mentees, collaborators, and even now, I should say, my mentees, collaborators, and all of us have had the privilege to use and do research at multiple user facilities located at not just LBL, but also other user facilities at the Lawrence Livermore National Lab, Pacific Northwest National Lab, the Stanford Linear Accelerator, and more. And I say this because I want to recognize that ESnet6, has always been this really important connection between the labs and the user facilities, right? And now ESnet6 is, one more important, ESnet6, is right now the more important step in the future to strengthen these connections that have been enabled and across user facilities and communities that we serve. Recently, I had the opportunity to join the Deputy Secretary, David Turk at DOE, and others, other colleagues at Oak Ridge National Lab to celebrate the launch of Frontier and to celebrate the dawn of the exascale era. ESnet6 is particularly important, obviously, at this stage as we enter this new era where we will be regularly producing exabytes of data that must be moved seamlessly between facilities, collaborators, laboratories, no matter where they may be. And ESnet6 will provide capabilities that are essential to support new kind of advanced scientific analysis, simulation models to meet national needs in addressing the climate crisis, transitioning to clean energy, and meet our economic, national, and energy security challenges. So I think it's not an statement to say that ESnet6 is truly a cornerstone of our national scientific infrastructure. And I'm honored to be able to join you today to celebrate this accomplishment. It is exciting to see how far things have come and what we've built together with ESnet. Thank you again, everyone, and congratulations to all.
To move on to our keynote addresses, but just like the ESnet6 project, we're a little ahead of schedule. So I'm going to do a quick check with our folks to make sure that are our speakers ready to go? Thumbs up. Okay. I'm going to start the introduction and we'll see what happens. So because we're really excited to get to our keynote addresses this morning. I'm really honored to introduce our keynote speaker, Dr. Vint Cerf, Google's Vice President and Chief Internet Evangelist. He is a true luminary. Referred to widely as the father of the internet, Vint co-designed TCP/IP, the foundational communication protocols that define the architecture of the modern day internet. Vint serves as a key advisor to a wide range of organizations, including DOE's Advanced Scientific Computing Advisory Committee, or ASCR. He's the recipient of numerous prestigious awards for his legendary work, which have had unparalleled global impact. Notably, he has received the U.S. Presidential Medal of Freedom and the ACM Turing Award, among many, many, many other accolades. Please join me in welcoming Vint Cerf.
Well, good morning, everyone. I hope I'm audible. Can I get indications that you can all hear me? Hearing nothing, says the deaf guy. He's hoping that everything is working properly. At least I'm unmuted, if nothing else. First of all, I'm in New York right now, so I wish I could be there with you personally, but it's the best we can do. And thanks to this technology, it's possible for us to participate remotely. I was very pleased to see that Senator Padilla and Representative Lee were able to participate in this opening of ESnet6. This is an astonishing accomplishment, but it's simply one of many that DOE and the ESnet team can claim. Some of you will know that DOE was among the first of the agencies in the research supporting agencies in the US government to adopt and implement the internet protocols after the ARPANET was built starting in 1969 and the internet was introduced in 1983 with the original three networks, the packet radio net, the packet satellite net, and the ARPANET. DOE recognized the need for and the utility of networking well before that, and they had already implemented the high performance physics network. But they adopted the TCP/IP protocols as part of their initiative to move forward into a highly collaborative environment. And they were joined, interestingly and nearly concurrently, by the National Science Foundation and by NASA. With the NASA Science Internet and the NSFnet backbones. Together with ARPANET, ESnet, those four networks became the core backbone of the American Internet, certainly in the research and academic community. And thanks to ESnet's efforts, we learned many, many lessons about what the academic and the scientific computing community needed in the way of resources and access and the ability to move information around among the various supercomputers. One of the motivations behind the internet design was indeed to connect a large range of users in the research community, several thousand campuses, to access to high-speed computing resources such as those that NSF and DOE jointly produced. So we learned quite a bit from that experience in ESnet's effort to support the users of that system. And you have just an amazing track record of high speed and capacity that ESnet 1, 2, 3, and so on have continued to produce. At this point, however, ESnet6 is really, in my opinion, a turning point in design and architecture. It has the capability to do much more refined resource allocation and I would say the configuration of its resources to support unusual, either very high speed or certain timely demands, the ability to adapt quickly at need. And that, I think, is an additional capability that the previous versions of ESnet have not had in nearly the same degree of flexibility. I have to say that this particular ESnet team has kept up with and in many cases pushed the envelope of commercially available resources. I can say at Google that we share this zeal for high speed. We're both looking at the 400 gigabit per second optical fiber capabilities per channel, and I know that we're both looking forward to 800 gigabits per second per optical channel when that equipment becomes more available. So all this tells you is that the ESnet team is absolutely at the forefront of networking capability and flexibility. So this is the thing that I find frankly astonishing about ESnet6 is that Inder Monga and his team have been able to implement this system, add new fiber and repurpose older fiber, and at the same time serve all the needs that ESnet 5 needed to serve and continued to serve while they were building ESnet6. And I'm sure, and I hope anyway, that Inder will give you more details about how this, changing the engines while the plane is flying was accomplished, because it is no mean feat to continue to serve a demanding community while literally introducing a dramatic upgrade, not only in capacity, but also in flexible architecture and management. So the fact that they could cut over to ESnet6 essentially without much visibility at all is nothing short of astonishing. On the other hand, we shouldn't be too astonished because Inder and his team are frankly the best you can get. And that's one of the reasons that DOE has continued to be such a leader in computer networking technology, as well as computer design and implementation for high-speed computation. The things that ESnet6 offer, at least as I see it, are some opportunities to explore terra incognita. One area of considerable interest to me and my company, of course, is cloud-based computing. And the ESnet6 actually offers an opportunity to explore what the relationship can be between the supercomputing resources that are available in the labs, for example, and the computing capabilities of cloud-based systems. The idea of interacting with the cloud-based systems, a sort of intercloud capability, from my point of view, is a very important opportunity to explore how to make that work. You can just think a little bit about the challenges here. Not only do you need connectivity between the cloud systems and the ESnet6 and the supercomputers that are supported by ESnet6, but you need to think your way through, what does this look like from the user's point of view? How does the mix of supercomputers and cloud-based services look to that user? How do we make the clouds compatible with each other? So that means some standardization is required. There's a big question about access control and the control of the data that is held either in the supercomputers or in the clouds or elsewhere. The idea of having some sort of inter-cloud-wide identity and authenticity is really important, not only for access control, but also for purposes of allowing a user of the of DOE resources to get access to the resources of other cloud-based systems and still use their common authentication schemes in order to identify users and what privileges that they have. And so I think ESnet6 is going to essentially force us to think about what identity is and what accounting is for individual users that will work across multiple clouds and across multiple facilities. And so being essentially coerced into solving that problem, in my opinion, is a good thing. This is like a lot of other standardization. Once it's recognized that you need this capability, it's good to have incentive to achieve the objective. So that's one aspect. The other thing that, of course, ESnet6 does is allow the various labs to share information with each other and share computing resources with each other. The thing which is particularly interesting about ESnet6, though, is its ability to dynamically allocate its resources to meet various and sundry kinds of demands, some of which have quite very high variation. In the case of large-scale data collection from an instrument of the kind that you see at SLAC or at the Large Hadron Collider, for example, you have to be able to ingest an enormous amount of data in a big hurry. But you don't always need to do that all the time, and so you need to be able to adjust and allocate the resources at need, and that's something that ESnet6 has introduced in a way that I'm sure we in the commercial community will obtain many lessons. So we are watching with great interest, and I hope participating in taking advantage of what you learn. And I'm sure you'll be willing to share that, because historically you've been a source of considerable insight into the design and implementation of systems like this. Another thing which I think is reasonably ascribed to the ESnet6 design is increased resilience in the architecture by the addition of more fiber optic links into the system, and generally the ability to steer resources around in order to either recover from failures or to adapt to demand. And these are the kinds of things that, as I see it, are important contributors to future developments that we will probably label ESnet7, whatever that turns out to be. In the meantime, it's an opportunity for those of us who are in the commercial networking space to learn from your experiences to the degree you're willing to share them, as you have in the past, and also to collaborate with you in order to find ways of adapting unique computing resources to the needs of the DOE researchers. And here I'm thinking about not only the supercomputer resources in the various laboratories, but the special purpose processing capabilities of some of the clouds, including GPU and TPU, the tensor processing units we have at Google for machine learning acceleration. And perhaps someday quantum computing. DOE and others are very much engaged in exploring the possibilities of quantum computation. And while we're nowhere close to having machines that will perform useful computations, we're certainly seeing some of the requirements that will drive the research efforts to get to those destinations. So to give you an example, it's pretty clear that in order to have a functioning quantum computer, you need to have more than one qubit, physical qubit per logical qubit in order to do error correction. Why do you have to do error correction? Well, entanglement doesn't last forever. And the problem of maintaining entanglement in order to complete a computation means that you have to cope with potentially degraded conditions over time. And that means you want multiple error correcting physical qubits in order to make up a logical qubit. And in some cases, it could be as many as 100 or perhaps even 1,000 physical qubits to make up one logical qubit. So if you need more than one logical qubit to do a computation, and you do, then we may be talking about hundreds of thousands, if not millions of physical qubits. We probably can't jam that many qubits into a single quantum computer. And so now we get into this question of, well, how do we build a machine of that scale when we can't build a single machine that way? And the answer, of course, is, well, let's build multiple machines and somehow tie them together. But that leads to this question of how to move entangled information in order to entangle multiple computers together, multiple quantum computers together. And that, frankly, implies the movement of entangled photons from one place to another. Many of you have heard the phrase, quantum internet, and I remember chuckling at the time, thinking, well, somebody just took the latest buzzword and stuck it on the front of internet. But the honest truth is that we do need that capability to move entangled photons between quantum computers in order to effectively entangle the computers together and build what is, in effect, a much larger quantum machine. Which means that the ESnet optical capability is going to be has to be applied to both of the problems. One of them is super high-speed conventional digital transport, but the other one is the ability to transport single entangled photons reliably and to essentially repeat them through repeaters. And I don't have to tell everybody in this audience that you don't just copy an entangled photon because the normal copying destroys the entanglement. So you have to do some very funny things called cloning, and we have to be able to do that using quantum relay systems. And so the ESnet6, in my expectation, is going to be an important avenue for exploring quantum networking in addition to the conventional networking, which it has already contributed substantially to. So if you're like me, you're going to be watching with great interest the experiences that the ESnet6 team have and share with the rest of us as they explore terra, as I say, terra incognita in the world of computing and communication. So congratulations again to the ESnet6 team on this launch, successful launch of the new networking services. Please don't stop there. We know there's more work to be done. And we know that while ESnet6 is running, that Inder and his team will be out there exploring what's at the edge of the envelope to bring us the next big thing. And I'll be around, I hope, to watch that happen as part of the Advanced Science Computing Advisory Committee. So I'll stop there with my congratulations. If I had a hat on, I'd take it off and tip my hat to you. Wish you well for the rest of this conference. I need to run off to yet another event here in New York. But congratulations again and best of luck.
All right, we're going to move on to our next plenary speaker. And I'm very pleased to introduce Dr. Ian Foster, who is the director of Argonne's Data Science and Learning Division, Argonne Senior Scientist and Distinguished Fellow, and the Arthur Holly Compton Distinguished Service Professor of Computer Science at the University of Chicago. Ian's research contributions span high-performance computing, distributed systems, and data-driven discovery. He has published hundreds of scientific papers and 8 books on these and other topics. Methods and software developed under his leadership underpin many large national and international cyber infrastructures. Ian has been honored with several highly regarded awards, and just 1 month ago, we all learned that Ian was named as the 2022 recipient of the ACM and IEEE CS Ken Kennedy Award. Please welcome Dr. Ian Foster.
Thank you. Thank you. I think you can hear me. That's good. So it's such a pleasure and honor to be here. I've been an ESnet fan since, well, the very early days. I don't think I was using it when it was ESnet 0, but certainly ESnet 1 or 2. And it's also wonderful to see so many dear friends and colleagues. Bill Johnston, who I learned so much from, Inder, Monga, of course, who's built this along with some help, I believe, but and many others. So thanks so much for having me here. So as we've already heard, if I can make this work, I bet I can. As we've already heard, is this turned on? Yeah, no, it's off. Okay, good. As we've already heard, DOE comprises a whole network of labs, 17 labs. I think I just heard 28 facilities. We'll get there eventually. Oh, there it is. Tens of thousands of users, thousands of scientists in the labs. Surely the largest resource in the world focused on research, particularly in the physical sciences. And for all these people to work together effectively, they need to be connected, sort of like we need a nervous system to connect our hands and our brain and our senses and so forth. And that's, of course, the role that ESnet plays. And what I sort of want to spend a minute sort of motivating why this is so important. And I thought I'd go back a little bit to the earliest example of team science that I'm aware of. And this is Mr. Eratosthenes back in 245 BC, who had the bright idea of measuring the diameter of the Earth. And turned out he was able to do so with an accuracy of within a few percent, simply by measuring the angle of the sun in 2 locations. It's Cyrene, now Aswan, and Alexandria, and the distance between those 2 locations. Measuring the distance is actually quite hard. It turned out back then there were people who were specialized at walking at a constant pace, and they would count the number of paces they used to walk from one place to another. How's that for a profession, I guess? But anyway, so team science, he was able to get a very accurate measurement by combining data from 2 locations plus the distance. It probably took a few months to do that. Didn't matter because the measurement was only being made once and then could be used for a very long time. A more recent example, Robert Fitzroy, some of you have probably heard of him. He was actually the captain on the ship that took Darwin around the world, but he also got involved in weather forecasts. He was using data being transmitted from weather stations across the United Kingdom, using the then new telegraph, so probably getting the data to him in a matter of at least hours, maybe minutes in some cases, and producing weather forecasts which certainly saved lives. They were controversial also at the time, but also gaining new knowledge about the planet. So he was the first person to realize by looking at the data he was collecting that there were these global, very large scale circulatory patterns that we now recognize as cyclones and other things. So 2 examples showing, the first one, data from far away, but collected very slowly. Here, data from far away, but being collected perhaps within minutes or hours. Scientists have always wanted more data, faster data, and also more reliable data. And here's another example of to illustrate why those three different things are important. So here's the Pony Express, which went from St. Joseph to not far from here, Sacramento. It took about 10 days or roughly 1 million seconds to get a message. You could maybe transport a few hundred letters in that time, so you could move a few tens of kilobytes of data. The actual transfer rate is maybe, you might get it up to a byte per second if you took enough letters in one go. The reliability, which we just heard about, probably not so good. There were hostile natives and floods and I don't know what else. So not the ideal transport system. So of course, what ESnet has been doing since at least 1986, perhaps earlier, has been trying to improve on the Pony Express in various dimensions. So today we're at the point where the latency from St. Joseph's to Sacramento is probably a pretty consistent, roughly 12 milliseconds. So it's about 10 million times better. And thanks to many decades of work, this is a very reliable 12 milliseconds. It doesn't change from day to day or moment to moment, which is vital for so much of science if you want to get a measurement exactly at the time that you want it. Its capacity has gone up similarly to here we've got a terabyte link. Perhaps to get from Sacramento to St. Joseph, it might be around a few hundred gigabytes per second. But again, hundreds of millions times superior to that of the Pony Express. And the reliability, as we just heard from a previous, from Vint, is extremely high. All of these links are very carefully engineered, and there are many redundant links, so that it's very unlikely that data will not be able to get through. So these are all things that make what we can do with this system for science much superior. Oh, and one more measurement that's sort of interesting is, oops, sorry, too many buttons, is another measure which network engineers will appreciate. I've always liked it because it's very important in supercomputing, is not just the capacity of a single link, but what's called the bisection bandwidth, the amount of data you can transfer from one side of a network to the other side. And this has gone up by an amazing 100 million times in just 30 years. So a very richly connected network has been constructed. So what can we do with this network? I'm going to talk about something called smart instruments in a minute, but I'll just mention that something we just did very recently was replicate the entire contents of the Intergovernmental Panel on Climate Change CMIP archive from Livermore Lab to Argonne and Oak Ridge. And we just did it by starting a transfer and leaving it to run. It took 3 months. As things improve in terms of local connections, we'll probably be able to do it in days, but the fact that it was completely automated and moved this data without any human interaction was quite remarkable. But what I wanted to talk about for the rest of my time here is just is this question of what can we do that's different. Now we have this ultra fast, ultra stable, and ultra reliable network available to us. Of course, we can move more data. We can move data faster. We can talk reliably on video conferences most of the time. I guess Vint sort of broke up a bit at the end there, which is, I'm sure it wasn't running over ESnet, that part. It was probably the Google part of the connection. I think. What can we do? Well, now we know that the network can be totally relied on. We can start looking at using it to do new things. And I've coined this term smart instruments. You could use a different term. Basically, what I mean is the ability to put together things that might say, take a sensor. This is the Linux synchrotron light source at SLAC, connect it to a computer. This is the Polaris computer at Argonne Lab. Connect it perhaps also to a, this is a AI agent. I don't know, it's located in Florida for some reason, but it of course could be anywhere. And then use that to control the instrument. So this is something that people have been doing for many years, is doing real-time control of instruments, but typically within the context of a single lab. We can start now to put together these smart instruments using components located wherever they happen to be best available. The most powerful computer, the largest database, the smartest AI agent, etc. So why would we want to, I don't know why this keeps, why would we want to do this? Well, let me give you a few examples that of things that I or my colleagues have been involved in. So here's one in which it actually involves the LCLS at SLAC. We're interested in imaging materials, granular materials, understanding how they deform under stress, trying to understand causes of failure, one of the biggest obstacles to economic development in many cases, the high reason for the high cost of things like airplanes and automobiles. So you want, in order to do that, you want to be able to collect data in real time from these from this beamline, and then immediately, quasi-immediately detect the structure of the material, and then use that information to feed back for the next phase of your experiment. And how do you do that? Well, the way you can't do it using conventional computing, you use so-called AI or machine learning, using models that are trained on large supercomputers. And what the SLAC team has been doing is moving the data to Argonne National Lab to do the training. Takes about 5 seconds to move the data, 19 seconds to train the network, 7 seconds to move the data back. I got the things in the wrong way around there, but a total of 31 seconds, which means you can do these feeding back on the instrument every 31 seconds. We'd like to do even better, and with ESnet6, we surely can slash the transfer time by probably a factor of 10. We can slash the training time by a factor of 10 easily using next generation supercomputers. We can get down to probably just 2 or 3 seconds iteration time. And that will transform how we're able to understand these very important materials. So just to sort of raise up our level of thinking, what we're doing basically here is the user is defining a little flow, we might call it, comprising transfer, model training, deployment, and then we're going to map that flow onto the computers that are available to us in this distributed ESnet6 connected system. Another example, oops, sorry, where are we? Here we go. Another example, totally different field. The new Crocus integrated urban field lab is similarly collecting data, but in this case from urban sensors, satellites, and supercomputer simulations to provide forecasts of both immediate flood risk in urban areas and long-term flood risk, that could be used for urban planning and so forth. And this again has a need to define and deploy, with any luck. This is still on, I assume. Oh, yes, there we go. It came up, then it went away. All right. They're there. Don't move. Define and deploy these model training and other workflows in our ESnet6 connected infrastructure. A third example, which I don't know why I'm going to hold it like this now. Anyway, put it there. Okay, the third example, we heard it earlier about work on COVID response. So another example, again, using a synchrotron light source from the US Department of Energy, wanting to image COVID proteins at room temperature, which one can do using a new technology called serial synchrotron crystallography. It's a fascinating technology. I won't say more about it, except to say that you end up wanting to do a very large amount of computing to combine data from many measurements of your crystal, many small copies of that crystal, and then combine them in a way that lets you decide whether you've got enough data and can therefore move on to the next crystal, or you need to continue imaging. So we end up with another flow. See, my hands are not anywhere near it there. It was you, I saw you. No, no. So anyway, so let's move forward. So, which is what I wanted to do anyway. So the point I wanted to get, the final point I want to make, and is that these smart instruments, which have such power by linking with high reliability computing, AI data with sensors, we can express them fairly naturally in terms of these simple flows, but we then need to be able to map them onto the computers and storage systems and other things in our DOE-wide infrastructure. And this, of course, comprises dozens of supercomputers, large data stores, other things, each historically being a little island to itself. So various of us, Ben Brown is going to talk more about this, I think, pushing towards creating an integrated research infrastructure. We've tried this before and called it a grid, and we've tried calling it other things, but we seem to be at the point now with this reliable connectivity where we can actually create it. We've already got some pieces of this in place. A number of us, working with people at the University of Chicago, have deployed data mover services at essentially every national lab, most US research universities, many other institutions that will move data reliably and rapidly from one place to another, ensuring universal connectivity. And further to Vint Cerf's comments, this actually combines cloud for management and locally deployed agents for data movement, it's a hybrid software as a service system. We're starting to see people deploying task orchestration mechanisms so that we can, given one of the flows I've shown you, we can direct computing to the different places where computing has to occur, starting off at perhaps Slack, then moving to Argonne, then to Oak Ridge, perhaps back to put data in yet another location, and we can track activities as they go on. What we end up with it's at least in some facilities, this is the advanced photon source at Argonne, is a system in which essentially every beamline, every storage system is integrated research infrastructure enabled. So these are all little storage agents, all accessible over ESnet6. These are compute agents also accessible over that network. And these can be combined together to run any of these flows shown in the upper right to implement these smart instruments as we want to create them. Maybe I'll skip this slide. So, why I'm excited about ESnet6. Of course, I like to be able to move lots of data, like those climate data sets that were mentioned, and that is in itself transformative. But the fact that we can now reliably start creating these smart instruments is what I find really exciting, because rather than people having to assemble these things within each of, say, 60 beamlines at the advanced photon source, a comparable number of beamlines at many other facilities, they can quickly create and define and deploy these smart instrument flows and have them run reliably using whatever computing is available within the DOE complex, rather than just what they've deployed at their own local computational system. So I think that's going to drive a great deal of discovery and innovation. I would say there's certainly much more to be done. We're still in the early days of building and applying these new instruments. I think scientists have got to get used to how to build them. They need to realize now that they can just take advantage of ESnet6 connectivity. There's a need to reach what I say here, the white space, but I guess on this map, it's more the blue space. Of course, ESnet6 has a remarkable reach. It reaches to, I think we heard, 17 labs, dozens of other research institutions, facilities in Europe. But there are places, say, in the Great Plains where people are measuring environmental collecting environmental data relative to climate change, or people in small universities or colleges in other parts of the US. So we need to find ways to reach them as well. And perhaps we should be looking at high bandwidth Wi-Fi and satellite connectivity and linking that into ESnet6. Perhaps that's what ESnet7 will be. And then I'm also very interested in this notion of how we extend ESnet into the quantum space. So, Vint Cerf talked about linking quantum computers, and maybe that's what we'll end up doing. But quantum sensing is already being showing a great deal of promise. New ways of imaging, new ways of medical imaging based on quantum sensors. And a good quantum sensor will collect entangled data. You need to be able to transfer that perhaps to a quantum computer over a quantum network. So, smart quantum instruments perhaps are also something we should be thinking about. So, thanks very much.
All right, I think we're going to transition to hearing from some of those who have been instrumental in ESNet's history. So I'm pleased to be able to introduce Dr. Ben Brown. Dr. Brown is the director of the Facilities Division for DOE's Office of Science Advanced Scientific Computing Research, or ASCR program. A physicist by training, I'm surrounded by physicists, that's okay. His research focused on optical control of quantum systems and quantum information science. As the director of the scientific and the facilities division within ASCR, Ben leads the strategic planning, budget formulation, and operational oversight of ASCR's strategic national resources, including ESnet. Prior to this role, he served specifically as ESNet's program manager and has been key to the development and execution of the ESnet6 project. With that, I'd like to welcome to the stage Ben Brown. Thank you.
Good morning. It's wonderful to be here, and it's an extraordinary privilege to follow this morning's speakers and to see so many familiar faces, many of whom I haven't seen in person in literally years. This is obviously a moment of profound pride for the department. It's also a privilege, and with humility, I represent many people from Washington and from our site offices around the complex that have contributed to the success of ESnet. I want to begin by specifically heralding and celebrating the career of my boss, Barbara Helland, who's announced her impending retirement. She's been a stalwart supporter of ESnet and Berkeley Lab, and her mentorship and guidance through the process of ESnet6 and my career in the Office of Science has been significant to me, and I think to the ESnet enterprise. So this is a time for celebration. This is a time for reflection. So if you allow me to take a moment to get a little meta, there are several truths that I have come to know in my 14 years in the department, but have been really honed and refined in the extraordinary privilege of the last several years being in the Office of Advanced Scientific Computing Research and working very closely with our partners here at the lab and the Berkeley site office. So, well, number one is that it's really important to celebrate and reflect. And I'm so proud that the team here has put this event on. I know it's an extraordinary amount of work. I was talking to some on the way in, it feels a bit like a wedding. Or some sort of significant event, a rite of passage. And I think that that is absolutely a truth of the moment. I want to underscore that this moment is also about celebrating all who came before this moment. And the ESnet team is one that has been 35 years of people dedicating their careers to something bigger than one lab, one science, one calling. And that leads me to another deep truth that I've arrived at in being really a close student of you've heard about these user facilities in DOE. They're very peculiar beasts. I mean, these are really exquisite, very expensive, one-of-a-kind resources that thousands of researchers around the country and the world depend on, and expands their imagination about what might be possible to advance scientific discovery. And one of these deep truths that I've arrived at in my career at DOE and as a public servant is that infrastructure is people. I know that may sound cliche, but we're in an era of renewal. We have the bipartisan infrastructure law passed last year. We are at a moment in which, of course, there's deep division in the country. But when we reflect on the things that make our country great over its entire history, and in this moment, I think about the people here at Berkeley Lab and at ESnet and NERSC and ALCF and OLCF at Oak Ridge and Argonne that I work with every day, and the team at headquarters and the deep partnerships on which depend the progress that we make. And when we think about infrastructure as people, it's about careers. It's really about people making a choice to stick with it, to be committed to a calling in the collegiality and partnership. And I see that ESnet absolutely and very viscerally is something extraordinary that totally, and this is another truth, reflects our culture and our values. And so I'd like to conclude my remarks by going extraordinarily meta and thinking about the history of this laboratory. And it's just profound to be here with leaders of the lab today and some before, and those maybe in the future, in your future career paths. When we think of the history of the Department of Energy, and I give an orientation to new employees and new fellows in the department every year, and it causes me to take a step back and reflect, look at the slides, dust them off, think about how can I make this fresh. But one thing that's I come back to again and again and again is that the Department of Energy began because of a war and because of the extraordinary existential moment of Pearl Harbor in World War II. But the choice to create a civilian enterprise from that in the Atomic Energy Commission in the dawn of the nuclear age, and to consciously work to advance science for peaceful purposes and broad societal benefit are foundational to who we are in the Department of Energy. And a second component of that is that, of course, we've built up the lab infrastructure just here on this place, E.O. Lawrence, and this grand experiment of teams that needed not just the celebrated best and the brightest, but the best technicians, the best engineers, the best electricians, the best plumbers to come together and build the tools that could advance science. That is what the Department of Energy is all about. That is what our country is all about. That infrastructure that was built in the Cold War era was sort of the private purview of the government for quite a long while. If you wanted to use it, you had to know someone. And I've reflected many years with my former boss, Pat Damer, who's been an extraordinary mentor to me in my career, that it is not a given that what we have today is an open laboratory system where the campuses are open, and that the advancement of science depends critically on inviting people to throw their ideas forward, to take a risk, and to be able to use this open infrastructure to advance their goals for higher purposes. And so when I reflect on this moment of ESnet6 and its promise and what it means and what you've heard this morning from two incredible speakers with incredible technical depth, what it means to me is that the future is about a culture of even greater interconnectedness, of even greater openness, of the national laboratories continuing to be bonded even closer together and offering what they have to be more than the sum of their parts to advance science for the greater good for our country and the world. So with that, I conclude my remarks with the deepest appreciation and humility for what you've achieved and my extraordinary pride in so many of you and what you've contributed to this country. Thank you very much.
Good morning, everyone. I'm Jonathan Carter. I'm the ALD for Computing Sciences. I want to add my welcome to that of Carol Burns, to all our guests from the federal, state, and local government, our colleagues from other national labs, universities, and of course, Berkeley Lab staff. So first off, I want to congratulate the ESnet staff, both the project team, the organization as a whole, the management, for doing such a wonderful job here. I know there have been many, many challenges, particularly over the past 2.5 years, and I think you've done a really wonderful job. I don't want to forget, I also want to call out the operations staff at this lab for helping out in this project too. There are many complicated procurements, upgrades of engineering that all had to be completed too. I also want to thank the DOE staff at headquarters and at the site office on really coming together, as Ben mentioned, to make this a reality. Berkeley Lab in the computing sciences area is the home of ESnet, and we focused on supporting ESnet as it's grown its capabilities over the past years to become the DOE user facility that it has today. In turn, ESnet is central in the CS area strategy, one component of it called Super Facility, which actually is very similar to the ideas that both Ian and Ben described, that is providing a seamless connection between HPC computing resources, between sensors, between experimental facilities, so that the person using all these facilities together doesn't have to sweat the details about where the data is, where it has to go, how to get the best results the most quickly. And an example which is happened during the pandemic, connected with the exascale XFL project, was services provided connecting the LCRS2 at Stanford and moving that data to NERSC for rapid processing and a fast iteration loop of that. And those just a taste of things that will be coming. And that's not all. ESnet has had a very innovative history through, say, its science DMZ program. It's provided labs and facilities and connection points, a roadmap to provide more seamless data transfers to avoid security where it's not required, and generally accelerate the flow. In the area of network research, ESnet staff with partners are constantly developing new networking concepts that we think will become operational services in the years to come. Things like in-network caching for improving scientific throughput by taking a data set that might be very remote and caching it somewhere on the network for fast retrieval. They're also using artificial intelligence and machine learning for networking, applying techniques to optimize the current network infrastructure, to route large science flows in the most optimal way, to provide guaranteed transfers, and so on and so forth. They're also providing prototypes like the test deployment of a private 5G network in a watershed in Colorado State, which enables scientists to pull up data from sensors that might be floating in the watershed and take them back over the network for data processing. Right, I'll cut to the chase. Now for the ESnet6 presentation. It's my great pleasure to introduce our speaker, Inder Monga. Inder is the Division Director of the Scientific Networking Division. He's the Executive Director of ESnet. He came to the lab with over 20 years of data and networking research experience, and he's led ESnet, for the last 6 years. He's very well known in the DOE and NSF research communities for his work in QuantNet and NSF's Fabric project. And of course, he's responsible for driving the vision for ESnet6 and also its execution. So Inder, stage is yours.
Thank you, everyone. What an amazing set of talks today from Representative Lee, Senator Alex Padilla, Dr. Berhe, Dr. Brown, Dr. Foster, Vint, Cerf. So thank you so much for all being here. I know you have traveled great distances to be here. I'm going to talk about a little bit about the story of the ESnet. Talk about how science uses the network, give a little brief history on the upgrades, and then talk about the capabilities of ESnet6. But before I do that, I want to showcase a video, and there's a lot more that can be said by a small video than by words. So please join me in viewing this video, and then I will start my presentation.
Science begins as a conversation, a question, a theory, which sparks discussion, debate, experimentation, collaboration. This is the language of discovery. For a long time, those scientific conversations were limited by the speed of horseback, the telephone,
Mr. Watson, please come here.
The modem. Today, we are experiencing an explosion in communications, conversations, connections, creating a world where data becomes discovery.
No individual is alone responsible for a single stepping stone along the path of progress.
Today, ESnet's international network makes the path of progress faster than ever. Scientists can collaborate side by side while thousands of miles apart, Exabytes of data speed across time zones with the power of ESnet, a global laboratory. ESnet connects great minds to make radical breakthroughs that will change everything. Science is a conversation, a global conversation, at the speed of ESnet.
So thank you, everyone. So ESnet is a unique network, as you have heard from many speakers. It's a mission network. And what we are really trying to do is to remove the constraints of geography so scientists can collaborate widely. They can share data anywhere. They can access the fastest supercomputers no matter how far they are. And they can engage the brightest minds. And we build cyber infrastructure with the express goal of accelerating scientific discovery. And that's the vision that drives us. Now, science, like I've heard lots of examples, but I'll give you a few and repeat some of them. The Large Hadron Collider, which is the world's largest instrument, is built in Geneva. And the collisions that happen in that led to the discovery of the Higgs boson and the 2012 Nobel Prize. Over the past decade, this instrument alone has generated 280 petabytes of data from 40 quadrillion collisions. And I had to look up what quadrillion was. It's 1,000,000 billion or 1,000 trillion, so that many collisions. And this is over the last decade. Since 2014, ESnet has been exclusive network that carries this data transatlantically from this instrument to physicists at US National Laboratories, Fermi National Lab, Brookhaven National Lab, and physicists around the country. But this is not just about US physicists. They collaborate globally to analyze this data and get the insights that we have. Now, this instrument is going through upgrades, so this doesn't stay static. And in 2019, the amount of data produced by this instrument is going to go 10x. And those are the kind of things that ESnet6 was targeting or thinking about when being built. Now, it's not only about the large instruments. It's about the sensors that you heard about, the sensors that measure the environment, the sensors that produce data that allow us, or the scientists, to reason about the pressing societal challenges today. You heard about the Earth System Grid Federation, the data that is accessed worldwide, and it informs leaders, world leaders, on what climate change policy should be. These sensors collect data, but they have to be shared widely because you want other people to be able to verify your models, to access data and do their own insights. So you see this graph in front is from the ARM user facility where the users are worldwide and they download these data sets to do their own work. Now, this data flows internationally and nationally through collaboration. It's not just ESnet, it's collaboration with regional networks, national networks, worldwide networks, some of them who are in the audience here today and virtually. So it's a collaboration itself in networking that enables this to happen. And you know, networking is 24/7. In the night, these optical telescopes are scouring the sky, looking for transient phenomena. Not just optical telescopes, but radio telescopes are looking for echoes left after the Big Bang to understand how the universe was formed, how it is evolving, and what the future holds for us. So that understanding comes from all the data collected from these telescopes. This supernova of a generation was discovered by a Berkeley lab scientist. And that came from real-time analysis, near real-time analysis of data streaming from the Polar Observatory. We are currently collaborating very closely with the Vera Rubin project, with multiple networking organizations in South America and US to transfer the data from this telescope that is being built in Chile to SLAC for analysis. And in a couple of years, this should be ready to go as well. Now, ESnet is not only about exotic instruments or sensors. It connects all the DOE national labs. There are more than 70,000 national employees. And these national labs have researchers that are working on the nation's priorities of basic science and energy security. So all the research at those national labs uses the network. You have heard mentioned many times today from Dr. Berhe, from Carol, on DOE being one of 28 Office of Science user facilities. What we are is a data circulatory system for those 27 other DOE Office of Science facilities. And that's what we hold dear when we think of the network and when we plan on what services we should build. Now, we have been collecting statistics on the data flowing through the network since 1990. Cerf mentioned we've been around for 35 plus years. And this data shows us that traffic has been growing exponentially 60% year on year. This traffic had a minor blip in 2020 due to the pandemic when the labs and some scientific facilities were shut down. But the growth has resumed its normal course. For the past 12 months, we moved around 1.4 exabytes of data. One thing interesting to notice, since 1990, it took us 28 years to reach 1 exabyte of data per year, which was in 2018. That's when we hit that mark. And in a couple of years, we expect to be doing 2 exabytes of data per year. So that's how exponential growth works. And I want to say, this was one of the biggest drivers that drove the mission needs document that we wrote in 2016 to start the project off. I'm going to give you a little bit history of ESnet, repeat some of the things that Cerf said. ESnet was formed as a combination of MFEnet, Magnetic Fusion Energy Network, and HEPnet, High Energy Physics Network. This was formed in 1986. And at that time, we focused on the internet protocols as an organization, helped deploy them, make them stable. And the internet was commercialized in the mid-90s. And all the work that was done by ARPANET, NSFNet, and many other people here who were around that time to help make internet the way it is, a stable and growing internet that has supported so much economy and growth and functions that you see today. But then, since then, ESnet has been upgrading the network and tackling this growing exponential growth of traffic, but pushing the boundary of the network with each upgrade. ESnet6 does the same, and I'm here to talk about some of the innovations and how we have pushed the boundary in ESnet6. Before I talk about the network, I want to talk about the goals. There were 3 simple but ambitious goals that we started out with. The first one I think you have heard about a lot of times today. It is about managing exponential data growth. Now, we wanted to build an architecture where we could cost effectively grow the bandwidth as the data increased. And I think that's what we focused on. The second one is, as real-time traffic, streaming traffic from instruments or supercomputers happen, we wanted to make sure we increase the resiliency and reliability of the network. You cannot afford to lose data if you're doing an experiment and have to do the experiment again. These are expensive user facilities and expensive instruments. But we also knew with the advent of AI and ML and quantum information science that the way science would happen, the way scientists would build things like instruments, like Dr. Foster talked about, the smart instruments, are going to change. And we want the network to be able to be flexible, to adapt to the change, to be able to build custom things and custom services that scientists need. And so we had to build an architecture that would build flexibility, because we couldn't truly predict what the future has in store for us. But we wanted to be able to adapt to it and serve those needs. So let me talk about what we built. So from a bandwidth capacity perspective, we worked with our partners who are here, Lumen, Ciena, Infinera, Nokia, to build and light up 15,000 miles of fiber across the US, with 300 locations where ESnet equipment has been put around the country. And to offer 46 terabits of aggregate capacity. Now, this is the capacity as of today, but we have built capabilities and to advance and add to this infrastructure as the data increases. Labs now can get from 400 gigabits per second to a terabits per second of capacity at their door, depending on their need. So this kind of took care of goal number 1. For the other 2 goals, I want to talk to you about the architecture and what our ESnet architecture is about. But rather than give you a lot of technical details, I'm going to give you an analogy, and I hope that works for you. So we went with this network design from an Amtrak model, where you stop at every town and onboard and offboard customers, or in our case, data, to what we call an airline model. So we can go from any instrument to a lab with preferred non-stop, or maybe at most 1 to 2 stops. So that's what the model is, and that's what we call the hollow core network, because we don't try to stop all the way in the middle. Now, extending that analogy further, the smart services edge becomes like the first class lounge, where you can get custom services to make your data what you need. So if a scientist wants a certain kind of performance, low latency, or they want some reserved bandwidth, or they want to move data at certain rates, they can get that. Do they want optical channels versus IP-based channels? They can get that. That customization was built in the smart services layer. The monitoring and the measurement made sure that none of the data would get weather delays, which is we monitor the performance of the network, performance of the flows, to make sure that we can do the best performance we can out of the system. And the orchestration and automation, using that same analogy, helped us deploy new planes on demand, or create new nonstop routes as and when needed. So that is the design, I think, that Vint mentioned was a unique design that will help hold us well for the future. I'm going to talk a little bit more about this measurement and monitoring capability. With collaboration with AMD, and thank you, Gordon, for being here, we built a system that can look at every element of the packet that goes through the network, ingress, egress. That capability is not really available in commercial products or commercial networks today, that we know of. In most of the networks, we sample things. So we look at 1 is to 1,000, and I won't try to extend the airline analogy with TSA here, so please keep that away. But in this network, we can truly, if we want to look at every packet that flows through the network and get information and data off it. What we hope to build is more proactivity. So rather than you picking up the phone, like you do at home and calling Comcast and saying, my network is not working, we want to be able to proactively understand performance problems. It will help with cybersecurity and other applications that we have thought about and yet to implement. Now, let me talk a little bit about the orchestration and automation capability. In traditional networks, what happens is we log into each device, there is a nice interface, and there is automation, but we use cut and paste or human-designed configuration into the systems. When we started this project, we had a goal of changing how we operate and manage this network. So what we wanted to do was to give engineers an ability to do and spend a lot of time on planning upfront. So the engineer sits down, plans what they want the network to look like, designs what the intent is, what the service should be. And once that design is complete and vetted and finalized, it's a matter of a push button so that an orchestrator takes that intended service and instantiates it within the network by talking to the various devices, converting it into the configuration elements of their choice. This investment, we believe, will help with the integrated research infrastructure, what Dr. Foster talked about in terms of smart instruments, where an AI can automatically control an instrument far away. That is the power of this platform. And I want to show a little demonstration of that to you. This is going to be a live demonstration today. And I know all live demonstrations have got some risk, but we decided to go with the risk today. We are all among friends here. So what I want to show you is this tool, what we call the policy-based routing tool. This has been built on top of this orchestration platform, and it's one of the many tools that you have. And what this tool is, we add new circuits or we add, have errors. You want to be able to test the network. So we built a tool for that. But for purposes of this meeting, we're going to have an engineer configure 3 paths. Now, this topology is automatically generated. You can see it gets all the bytes on counters automatically from the network. And the engineer is selecting 3 paths to do 3 by 100 gigabits transfer cross-country. Once the paths are selected, all they hit is a commit button, and that automatically configures the paths, configures the traffic generators, and gets the traffic going. And this is something that we wouldn't do hand selection in many cases. In many cases, we just select this link needs to get tested, and it computes the paths and sets up the testers and does all the configuration automatically. But because we didn't want to bring the production network down, it was an ESnet6 Unveiling event. We wanted to make sure we chose the right paths so that we could saturate it without causing any issues on the production traffic. So can we go to the live view? Okay, so this is our platform. It's called Stardust. It's our real-time monitoring platform. You can see traffic starting at the edge as this commit was made and the network got configured. The links are going to turn blue as traffic reaches 100 gigabits per second, and you can see that happening. Now, this tool is built on our telemetry platform. Each of the elements in the network is giving us telemetry that is actually streamed to a Google Cloud, where it is analyzed and then visualized. And that visualization is what you see. This is something that the engineers use. We use with our partners. There was a big LSC data challenge, and the physics folks were using this to see how the traffic was going, what flows were going over our network. And this is kind of a real-time platform that we have built within ESnet as well. As you can see, the traffic is going up. It is now at 200 gigabits per second. And in little time, it will reach 300 gigabits per second. You can see it coming up at 300 gigabits per second. And the lights are lighting up. What you have to realize that this is amazing. In a few minutes, we were able to configure paths across the country. While I was standing here, was able to get the traffic started and do a 300 gigabits per second flow that moved around 3 terabytes of data while we were just chatting here. And this is the capability of ESnet6. And we want to be able to move petabytes of data and hundreds of petabytes of data at a push of a button. And that's what our goal is. I'm going to move on to the slides. I really want to thank the engineers because they've worked well and the switching happened, but also we had a whole backup plan. So if this didn't work, there's a recorded video that you can see showing this happen. So amazing. So lo and behold, I give you ESnet6. I think, as Ben mentioned, this is not just about technology, it's about people. And I really, really am thankful to the people that made this happen. They're all here, sitting with you. .413.3 processes. But this was the first time for the facility to do that. And it was a steep learning curve. It was not easy. I remember how we all felt after the first director's review. But the team learned, they tackled this, they embraced this, and they made sure we use this process to get done the project completed ahead of time and under budget. And that is just amazing effort by the team. It was the first greenfield build of a network. We hadn't built the network from scratch and integrated it ever before. We used to get services from carriers and build some of it ourselves. It was the first time we built completely the optical layer and integrated that. When we started, we didn't have all the people to build this network. So we were hiring, integrating, and building the team. And we grew the team more than 50% while we were executing the project. And then we had a surprise, the pandemic, right? And that increased the coordination 10x. I mean, we had to go to the national labs, to different sites. During this whole time that we implemented the whole optical network, actually during pre-vaccine pandemic period, there was not a single recorded direct transmission due to this installation. And that was the amazing work done by this team. And we had to do all of this while making sure none of the labs really felt that we were upgrading the network. They wouldn't even know that we had, during the project, taken elements of ESnet6 and moved it into service. And we did that constantly throughout the project. It was not build and then switch. It was building pieces of it, making sure it's stable, moving it into production, tackling the next piece. And that's how we built that engine while it was flying, as Vint Cerf mentioned. Now, this amazing feat is what I'm here to celebrate. This amazing feat is why ESnet folks are here among us. And I really appreciate and I'm humbled that all of you flew in and came here to watch us celebrate this event. And this is the people of ESnet that all worked on this project. And I would like to And while I'm humbled by the mission orientation of all of ESnet staff, I do want to call out two folks that actually led this project, Kate Mace and Patty Gentili as project directors. And I want you to raise your hands. I won't ask you to stand up. I also want to thank all the people who supported this journey. And there are too many people to name, and I'm sure I'm going to miss someone. So I apologize in advance. I want to personally thank the ESnet program managers of DOE who supported us, who trusted us and believed in the vision. And it was Vince Titoria who started out with the mission need, Dr. Ben Brown, and Dr. Carol Hawk, who's online virtually today. They have been amazing supporters. And not only that, Rick Chapman from the DOE Berkeley site office was a stalwart believer in the team and what we were doing. I want to thank the lab leadership. Without their support, this would not have happened. I think we talked about finance and procurement and all of these important issues that needed to be tackled, and during the pandemic as well. So I would like to thank Dr. Mike Vidrell, Deputy Director Carol Burns, Deputy Director Michael Brandt, Dr. Ho Simon, who's not here physically with us, Dr. Kathy Elikshi, her support was amazing, Dr. Carter, the lab project management office, the finance team, the project management team, all of them. But you know, the project had mentors as well. So it was not just us, the DOE and the lab. We had a lot of reviewers who spent their time and energy to help us figure out what we were missing, what we were not seeing. And some of them are here in the audience today. Sandy Marola, Phil DeMar, Eric Lancon, I think he's here as well, and Amber, thank you. Thank you for giving us your insights and expert advice that helped us be better and helped us be successful. This kind of mission orientation and careers of mission orientation is very hard to find. So I truly, truly thank all of you from the bottom of my heart, all the ESnet staff here. Can you please raise your hand so others can see who the ESnet staff are, please? This is truly a celebration about you and your accomplishments. With that, I would like to thank you. And I would like to invite our vendor partners. Without their help, this would not have been accomplished because they were with us, supporting us steadfastly through this thing. So first, I would like to invite of the vendor partners, Steve Alexander, who's leads of vision and technology for Ciena, has won several industry honors, including the IEEE Communications Industrial Innovation Award. It's my pleasure to welcome Steve to say a few words. Steve, thank you.
So Inder and the team, I think I just got to start by saying congratulations. That is fantastic. I can tell you there's a lot of folks that would see that connectivity on demand capability and want it immediately. Right? That has been the dream of many organizations for years. But I do want to just take a moment and say why I think it's so important that these kinds of collaborations exist between industry and the research side. When you're in the commercial world, that's what we are. We build, commercial kit. It goes out into all the large networks all across the world. Ciena was first to do WDM. We're the first to do coherent detection. Those are the kind of typical technologies that are out there now. But those are all largely what you might call scale out opportunities. It's how do I get video to everybody's home? How do I get fiber out into the neighborhoods? How do I connect up cities and towns and build metro networks and stuff? Obviously very important, right? This is how the world communicates. It's the circulatory system of the internet. But then you meet folks like Inder and yourself, right? And you see numbers out there that start with exabytes. Now I had to go look that up when he first brought that to me. I'm going exabyte. Okay, I know that exists, but I got to exactly what exponential is that, And so what the research world brings to us is the ability to scale up in ways that we just wouldn't otherwise get that opportunity. And so it's critically important that these kinds of collaborations exist. I can tell you it has been a personal delight to see what's been accomplished here. I mean, you got to take me back to, a 15-year-old kid who figured out with a helium neon laser, he could send Morse code across the street. Okay. And see what we've been able to do here with these technologies. It's personally hugely rewarding. I look at the team here that you put together, Inder, and again, congratulations. And again, in the spirit of scaling up, all I can say is, okay, all right, my friend, what's next? Come on.
I would like to invite Robert Maher, who's the CTO of Optical Modules and Coherent Solutions. Infinera worked very closely with us in the installation of the optical line system. So please welcome Rob Maher.
Thank you. So ESnet's strong vision for leadership in networking innovation and software automation that we just see draws many parallels with Infinera's vision and Infinera's mission, which is to revolutionize telecommunications networks. And we do this through innovative coherent technologies, systems for network infrastructure, and automation software for the control and optimization of the networks of the future. Our differentiation stems from our leadership in the design and US-based manufacturing of these vertically integrated solutions, which are built upon our photonic integrated circuits, digital signal processing ASICs, analog electronics, and an app-centric software suite for automation and reduced operational complexity. Again, something that draws many parallels with what Inder just demonstrated. This technology stack ensures that we can maximize capacity across any of these fiber optic links, while supporting software reconfiguration and advanced telemetry features to keep a pulse on the health of the network. Our pursuit to continually challenge conventional thinking and to develop truly differentiated products is in close alignment with the groundbreaking research prioritized by the DOE Office of Science and ESnet's vision for the underlying optical network required to support major scientific discovery. We're very proud of the partnership we've had with ESnet over the years, which has evolved as the network has evolved. A decade ago, back in 2012, we were deploying 100 gigabit Ethernet services using our TTM platform. And today with ESnet6, we're deploying our Flex ILS C+ L-band optical line system and our GX compact modular optical transponders. Scientists will benefit from one of the most advanced optical networks in the world, built on 15,000 kilometers of dedicated fiber and 46 terabits per second of capacity. And what's truly amazing, what Inder just demonstrated live, is that this can be dynamically provisioned around the network. This optical superhighway will provide a more efficient platform for scientific discovery and support critical research that relies on the generation, transmission, and processing of large data sets, such as genomics, energy, high-performance computing, and quantum information science. So to conclude, I'd like to congratulate ESnet, the DOE, and the Lawrence Berkeley Lab on behalf of Infinera. And we look forward to the groundbreaking research that ESnet6 will produce. Thank you.
Thank you. Next, I would like to invite Mike Loomis, who's the general manager of Nokia Federal. He leads Nokia's engagements with and product investments, and he has a deep understanding of technology. And he was working with us in ESnet 5 as well, so please.
So thank you, Inder, and thank you to the ESnet team. It's really an honor to be here. And it was a pleasure to be involved, I think, almost a decade now with ESnet. Very, very proud of that. ESnet's a different kind of networking experience. First, it's a different kind of network, and it's not something you get to do every day. It's a meaningful venture with really meaningful applications. And as I was packing to come to California, my wife says to me, "So, honey, what are you going to do this week in California?" And I said, "Well, funny you should ask. We're going to go to the commencement of a network that transports experimental data from the Large Hadron Collider back to physicists. Oh, and by the way, this same network also takes X-ray crystallography and transports that back to NERSC to help decode the SARS-CoV-2 virus." And that's not something you get to say you do every day in this industry. And it's certainly more gratifying than working on solving the problem of making sure a streaming service doesn't pixelate or the social media screen scrolls down very quickly. Our role in this network, we're the router, so I get to sit between my colleagues from Infinera and Sienna. We take the packets off the optical network. We look at those packets. We decide what the best path for them to get to their destination, and then we ship them down their way. Our usual role is in large telecommunication service provider networks, and they select us for reliability and performance, but really it turns out that usually they buy our routers as an insurance policy because they never really get maxed out except during systems tests and certification tests. And that's not true with ESnet, and that's one of the reasons why we really love being part of this, is we get petabytes of data thrown at us at line rate, and the router has to perform, and that's not easy for a lot of reasons. And I started thinking about this, all of what had to happen to get this state of art of equipment, not just from Nokia, but from all our partners here to deliver this capability. I'm like, wow, all right, that's pretty interesting what went into this. So if we look at the 7750 router, it's a 56 terabit per second router. It supports 400 gig interfaces, which are just astounding to me. Thinking back at my early career, worrying about getting a 10 megabit Ethernet interface going. Those 400 gig interfaces can support 800 gig today as soon as the commercial optics are ready, and we've shown it to transport terabit flows over our own proprietary optic, and those are strange looking cards. And a lot goes into that. You can't do that. This is, to accomplish that, you're processing billions of packets per second. Each one of those packets you have to take, look it up, take stats on it, decide where it needs to go. Sometimes you decide this packet doesn't belong here and you need to drop it. And that wouldn't be possible without an ASIC development to support this. And that takes a very long time. A lot of people work into building those ASICs, packaging up into the system. And for these particular ASICs, to handle that kind of capacity, we had to solve a few hard problems, a couple of interesting ones. We solved them down the street in Sunnyvale, California. We do the design and R&D for the system and the ASICs, but we had to get 56 gig SerDes working. And that's how to get bits off the wire and the traces on the circuit boards on and off the ASIC, which turns out is one of the hardest problems at operating at this kind of capacity. That was a problem we solved. Another problem is to operate at that speed for billions of packets per second. We needed to have memories that were much faster than commercially available. And we had to design our own memories, very high speed memories, to take that information on and off the chips to do these very fast lookups. I thought about all that and I think, well, isn't it awesome that all that research and development went in to provide a network to provide this kind of research? So thank you for letting us be part of that.
Thank you. Now I would like to invite Gordon Brebner, Senior Fellow, Adaptive and Embedded Computing Group. Thank you, Gordon. Yeah.
So hello, everyone. It's great to be here, and congratulations, Inder, on this technical triumph being unveiled today. And being from AMD, I'm surrounded by the giants of optical networking here. So you might think, what's AMD got to do with this? And it's actually an excellent example of kind of industry government partnership in the research. 4 years ago, we started a little research collaboration here, facilitated by Inder. I'll mention Yatish Kumar here in the audience of ESnet, and Chris Neely of AMD here have been instrumental. And basically, we were looking at what would happen if we added adaptive computing technology or FPGA technology, which is our bag, into the network. And that led to what Inder revealed as the packet microscope, enabling you to look at every packet and just analyze what's going on, diagnose the network, dynamically adjust the loads. And this came out of what started as a little research collaboration. And now we have the technology in every node of ESnet6, which is tremendous, from my point of view. But going beyond that, Ian mentioned the smart instruments, etc. Now we've moved on the research collaboration, we've got into the production network, into what happens at the endpoint. And what we're looking at is, ESnet can deal with fire hoses of data for sure. That's why we're here today. But there's even more data coming off the instruments. So working, for example, with the advanced light source here at Lawrence Berkeley, we're looking at using the adaptive technology to filter and distill data before it even gets to ESnet. And then at the other end, at the supercomputing, looking at doing load balancing. This is in the Jefferson Lab, for example, load balancing the data that's coming off and heading for supercomputers. So really, it's the beginning of a mission for us. It's in the network. We have the flexible technology, for the 10-year or whatever lifetime of the network, we can change things and adapt the hardware, which is my business. So it's a real delight to be here. AMD was very proud a few months ago to be powering Frontier, the first exascale supercomputer in the world, and now to be here today also with AMD helping to power ESnet6 really puts the pieces together. So congratulations, Inder, and everyone in the room, and especially Yatish, my best friend and collaborator here at ESnet.
I would like to go to Lumen. Zain Ahmed is a Senior Vice President of Lumen Public Sector. He's joining us virtually live. So I don't know if the control room can get Zain on screen.
Good morning. I'm excited to join this impressive lineup of speakers this morning for the unveiling of the next generation ESnet, ESnet6. Thank you, Inder, for the great presentation and tremendous leadership. I know this was really hard to work through during COVID challenge times, and the supply chain was not any easy task to work through. What is Lumen doing? Lumen has been a long-time provider for ESnet and providing the high-speed fiber backbone that lays the foundation for the ESnet, which is laid up on. So our co-location data center and fiber connection act the building blocks that enable ESnet to expand its 15,000-mile network faster with increased capacity over time as data demands continue to grow exponentially. As Inder has noted, ESnet has experienced an amazing 60% annual growth in network traffic over the last 30 years, and which now ESnet has ability to offer 400 gigs to 1 terabyte service. That's pretty amazing for an education network to be able to move so quickly. And he just displayed to us like how quickly they can actually provision these services. And ESnet has long served as the department's data circulatory system that connects tens of thousands of DOE-funded researchers, not only with each other, but also with the global research and education institutions like the CERN Super Collider in Geneva. As a company, we're committed to doing our part and happy to support DOE achieve its mission. And we'll continue to be part of this great mission and making sure that breakthroughs in innovation and scientific research continue to happen. Thank you for having me. I apologize for not being there in person, but happy to join virtually. Thank you, Inder.
Thank you, Zen. Hello, everyone. I am honored to introduce our next speaker, Dr. Anne Almgren. She's an applied mathematician and a senior scientist and the department head of applied mathematics at Berkeley Lab. Her primary research interests are computational algorithms for solving partial differential equations for fluid dynamics in various application areas. In 2015, she was named a Society for Industrial and Applied Mathematics SIAM Fellow. She also serves as the Deputy Director of the Department of Energy's Exascale Computing Project, AMREC's Co-Design Center, and is a member of multiple ECP teams, including the ExaWind project, which is her topic of discussion today. Please join me in welcoming Anne Almgren.
Thank you. So I want to start by saying I know several people in ESnet. My office is down a flight and over there. And I feel like today I finally have an inkling of what you do. So, to echo a couple meta comments, one of the greatest tributes I can give to ESnet is I never really thought about it, because I'm one of those scientists that wants to do science and doesn't really think about the infrastructure. I actually work in software infrastructure, so I know what it's like to go under, unseen and unrecognized. But it really is a tribute to ESnet that people like me have been able to take it for granted. So on behalf of all the people like me who take you for granted, thank you. So in the nature of a historic, and this is now, so we've transitioned to the science talks. I'm not going to talk about networking. I probably won't say byte other than I just did. So a little bit different perspective. The title of my talk, let's see, I guess. There we go. So the title of my talk is ExaWind and ESnet. ExaWind here refers to two things. It is the project name of a project that is part of the much larger exascale computing project. It's also the name of a code suite, and aspects of that are funded by the DOE Wind Energy Technologies Office. And so I want to acknowledge both the exascale computing project and the EERE Wind Energy Technologies Office. So a little bit of retrospect, well, looking back a little bit here, not trying to step back. So the question is, when did we first start using wind energy? And of course, you have to define using wind energy. There were sails and sailboats a long time ago. There were windmills pretty far back. So at least 1,000 years, there's evidence that people used windmills to, and of course, they were using mechanical power. There was no electricity. So they were using them to do things like pump water and grind grains, basically. 1850 is significant. It was the first US wind engine company. So somebody decided this was a good idea. There were something like 15 different turbines showcased at the Chicago World's Fair in 1893. It wasn't until 1941, that was the first time that a wind turbine in the US was used to feed into the electrical, well, what was the electrical grid, and it actually powered homes. So 1941 in a place called Grandpa's Knob, Vermont. And one of the questions I'm going to talk about is, how do you decide where to put these? And if you're in Vermont, you happen to know that there are local high spots and low spots, and it's windier on the high spots, as anybody who's hiked in the White Mountains or the Green Mountains. So they put it on top of a knob. But one of the other constraints is you have to be able to get all the parts there. And so one of the reasons they put it there is there was a road that could get them there. It was a relatively short road. It was a peak. So forgot the name of it, but anyway, Grandpa's Knob in 1941. Now, of course, we come to 2022, and if you live in the Bay Area, you drive past the Altamont Pass, windmills or wind turbines are something that you're very used to seeing. So in 2021, about 9%, over 9% of the US Total electricity generation was with wind power. Wind power surpassed hydroelectric in, I believe, 2019. So again, relatively recent. And again, in 2021, the capability was about 136,000 megawatts. So keep in mind, that's about 1/7 of a gigawatt. Okay. One of the things that I want to convince you today is that this is a really exciting time to be working in wind energy. And if you look at this historical past, you say, well, what's changing? Well, what's changing is the advent of offshore. And so, we were talking about 1,000 years ago, 100 years ago, the first offshore wind farm was in 1991. So Vindeby was a Danish wind farm. It's since been decommissioned, but that's really only about 30 years ago. First US offshore wind farm, it's called Deepwater Wind, it's off the coast of Rhode Island, 2016. So that's 6 years ago. First floating wind farm, Scotland, 2017. Now, the thing that you'll see that's missing there, which I wanted to make sure, when's the first US offshore floating wind farm? Hasn't happened yet. So about a month ago in September, they announced the floating offshore wind Earthshot. And so this is a new push. And so when I say it's an exciting time to be working in wind energy, this is why. Things are changing, they're changing fast, and there's a huge opportunity here. So the federal government has mandated 30 gigawatts of new offshore wind energy by 2030. So remember, we had about 1/7 of a gigawatt. 2021, this is now over about 220 times as much. And in fact, in addition, the Earthshot is targeting 15 gigawatts of floating offshore wind capability. So why is this different? So most of the 2030 goal was fixed bottom. Why is floating such a big deal? Well, especially if you live in California and you look at what happens to the bottom of the ocean as you go offshore. On the East Coast, you've got a kind of a ramping area. So there's places to put your wind farms. Off the coast of California, not so much. So floating is really a necessity here. And again, it's just been announced as one of the Earthshots. There are various trade-offs to offshore versus onshore. There are societal impacts, there are environmental impacts, there are a number of things. So today, I'm not going to argue pro or con with those. I just want to talk about the science, because that's what we're working on. Okay. So one of the things that I didn't fully appreciate when I first started looking at wind energy, and again, I'm involved in this ExaWind project that is about modeling wind turbines, is just how big they are. So this one, Windfloat Atlantic, is off the coast of Portugal. The blades on these have these three 8.4 megawatt blades. The blades are 82 meters long. So these are big. Typically, when we think of these wind turbines, we think of the top part, right? We think of the rotor, we have the hub, and we have these blades, and they're really kind of beautiful as they spin out there in the blue sky. But there's this other part, and one of the things that was significant about this one is it was the first, the semi-submersible base. So here's a picture of the base that they're going to load onto a boat and take out there. So these floating platforms, they're 30 meters high. Most of that's going to be submerged, and 50 meters aside on that triangle. So these are very, very large objects, which means the designs that worked for the smaller windmills originally and the smaller wind turbines don't necessarily scale up. Let's try that again. And they're only getting bigger. Okay, so if you look back there, you're about 0.2 megawatt. You can tell when you go from between US sources and European sources, we go between meters and feet. So this one's now in feet. But if you look at the land-based wind, there's a time axis on the bottom there. We're between now 2016 and 2035. And you can see these things are just getting bigger. So there's a huge opportunity, but there are a number of challenges. Okay, why is bigger better? So if you look at the power formula for wind turbines, it scales with the area that's swept out by the blades. So longer blades, you get a squared factor, pi r squared, size of a circle. The other thing that happens is the power output scales with the cube of the velocity. Okay, and one of the things that typically happens is there's a frictional effect as wind goes past the ground. If you put a windmill or wind turbine very close to the ground, you have a slower wind speed. Typically, on average, as you go higher, you get faster winds. And so with that cube factor, if you double the winds, you've got 8 times the power output. So we want to maximize the output per turbine. And one way of doing it is making them bigger and taller. Okay, so hopefully I've convinced you this is kind of a big problem. Okay. Sorry. All right, so what are the questions? So I'm actually in the business of research, not design, but the ultimate goal of the research is really to be able to deploy efficient wind turbines. Okay, this is a picture of the Altamont that those of us who drive past there know very well. So to design the next generation of wind farms, there are questions we need to answer. We'll see how fast these appear. So one of the big questions is, where do you put it, right? And you've seen videos. There are wind turbines on ridges, on peaks. There are wind turbines in valleys. There are wind turbines in the ocean. So to understand where to put it, you have to understand the characteristics of the flow in the location where you want to put it. So that's obviously a very important question. That's the Altamont Pass. The size and shape of the blades. There's a whole engineering problem associated with these shapes. We know how much money companies like Boeing have put into wing design. So the shape of these individual turbine blades has changed dramatically in the last 30 years. That's a big question, not one I'm going to answer here. Okay, how many turbines and in what configuration? Sometimes you'll see them stretched out in a line. Sometimes you'll see them in kind of a grid pattern. What determines that? Well, we're going to talk about that. And how many turbines there's something like 4,930 turbines at the Altamont Pass. Another question that I'm not going to answer, but it's very important, is once you have this in place, how do you control this? There are a lot of variables. There are a lot of ways to optimize the power output. This is a big problem. And then finally, something that's come up even more recently, we're all aware of recent weather events and more of a focus on this becoming our new norm. If you're going to build these wind turbines and you're going to put them out in the ocean, you'd like to know that the first hurricane that comes along isn't going to take them out. So that is an increasing question of interest. This is Fiona, by the way, who went right up the East Coast, as we know. Okay, so there are two ways to answer these questions. And this is common in science: data, 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 data. Let's go out and measure. If we want to put a wind farm somewhere, let's go out and measure. Okay, when somebody first told me about buoys, I pictured the little things that you drop in the water so that a sailboat knows which way to go. No. This is what they call a buoy. And so they put these out in the ocean to measure things like wind speeds and the characteristics of the air. So data is being collected. There's a lot of work being done to collect data at different sites to be able to profile what the wind patterns look like there. So collecting the data, it's time consuming, it's expensive, and even more important in some sense, it doesn't give us the full story. And anybody who works in an experiment knows this, that if you imagine that you can sort of see this as an idealized wind farm there, you might space these buoys out. They're expensive, so you don't have that many of them. Maybe you space them out every couple kilometers, and maybe within the wind farm, you space them out every kilometer, maybe outside the wind farm every 10 kilometers. You have data at those points. You have zero data in between those points. And so that's one of those differences. Data, to me, data is truth, right? Assuming we've got the right kind of instruments we're interpreting, that's truth. Nature is doing its thing. We're observing it, but we don't have the in-between values. And so, there we go. And so people like me look to the answer through modeling and simulation. So what I mean here by modeling and simulation is computer models that we take we try to figure out what are the most important processes. We write computer codes, we discretize these, we run them on computers, and we ask, what's the wind doing? And one of the things that I'm hoping to come across, if this is a simulation of 4 wind turbines, there's a lot of simulation data there. We've filled in all the pieces. So if we can believe our simulations, we've got a whole lot more information than we do from the data. We absolutely need the data in order to trust our simulations. The other thing that I want to take a moment to comment on is when I gave the example of how we distribute the buoys, maybe every 1 kilometer resolution within the wind farm, every 10 kilometers, that's a variable resolution. So it's what you could imagine that looking down from overhead at the buoys. In the simulation, it's hard to see. When we look at visualizations, we see a picture and you can't really tell what resolution this was run at. It's not so coarse that you're looking and say, there's the individual data point. And this is actually really important in what we're doing. I'm going to talk about this more later. Okay, so this is not an either or, we need both. And as in most scientific enterprises, the data and the simulation together are way more powerful than either by itself. Okay, we were there a minute. Okay, why is this a hard problem? Wind flow over a flat plate, we're pretty good at that. People have been doing fluid flow calculations for a long time. So what makes this problem harder? So one obviously is we have a variable terrain. What are the effects of complex terrain? They can be very benign or they can be very, very dramatic. Offshore, what are the effects of waves and coastal effects? So depending on how far out we're putting the turbines, they still feel the effect of being near the coastline. The waves change something we call the surface roughness that changes the profile of the wind as we look up. So if you get the wind wrong by a factor of 2, again, that's almost an order of magnitude in wind power. How do the turbine wakes impact each other? We'll see that in a minute. And then the bigger question, how does these weather patterns that may be global patterns, how are they going to affect the weather weather behavior outside the farm that's going to come inside the farm that's going to affect how that individual turbine spins? So these are things that we all want to figure out. I apologize for the delay here. Okay, so this is what we call a multi-scale problem. And that's a word, we throw around the multis, multi-physics, multi-scale, multi-rate. It really is a multi-scale problem. Here I'm going to focus on the length scales. So again, you can see the global scale. That's where these weather patterns are formed. In the work I do, we're not resolving the global patterns, but that's really, if you think about the definition of the problem, we go from global to mesoscale, like the continental US, for example, to individual plant scale, to turbine scale, to blade scale. So if you're going to do predictive simulation, where by predictive simulation, we do validation by doing a simulation, trying to match existing data. We know what the data was, we try to match it. Predictive simulation means we want to play the game of what if. We want to predict something that didn't happen. We need to validate first, but to do this, we've got to resolve roughly 8 orders of magnitude. And so when I talked about this, when you look at the picture, you don't see what scales the solution is being simulated at. I'm going to try and convince you that that's a very important part of this problem. Okay. And again, I mentioned that this project has been funded both by the Department of Energy Exascale Computing Project and by the Atmosphere to Electrons project that's part of the wind energy technology process. And if you look at the goal of the ExaWind project, to advance the fundamental understanding of the flow physics that govern whole wind plant performance, including wake formation, complex terrain impacts, and turbine-turbine interaction effects. And the challenge problem, which will be solved in the next year, is 40 wind turbines in a 50 square kilometer area. So this is getting pretty darn realistic. Okay. So let's start with a single turbine. That is a 2 megawatt turbine that's sitting at the NREL facility in Colorado. You see here in the red is mesh. There's some gray lines that are a little bit hard to see in the upper. Those are the blades. The red lines tell you how fine a mesh we're putting around those. That's for those that do this stuff. That's an unstructured mesh that fits this very, very tightly to resolve the boundary layer on the edge of the blades. So that's what we have on the inside. And now if you look, you'll realize that that's embedded in what looks like black boxes. So those are, if you're looking from the outside in, those are increasingly fine meshes, which again, when we talk about resolution with the buoys, it might be 1 kilometer apart or 10 kilometers apart. Here we're going from sub-millimeter scale up to meters and tens of meters. And that's what these unfortunately, the way it comes out with the black and gray, we're doing this nesting that's going to span these 8 orders of magnitude. So this is how we resolve one turbine. But of course, the turbine doesn't live in isolation. Okay, next. Can you do next from there? Can you do next? Oh, there we go. Okay, so this, we actually don't just care about the flow right at the turbine. That's what's spinning. It's going to create the electricity. But again, we're not solving one turbine in isolation. So that was a zoom in of that turbine blade. What we're seeing here is the wake behind it. And we're graphing the velocity in the plane. So it gives you can think of it as vorticity. You can think of it as the pattern, the air that's coming off the tips there. So that's that. And then let's see if we can see. And this is embedded in a much larger simulation. So this is this idea of nesting, of being able to use resolution. It turns out if we tried to run everything at the fine resolution, it doesn't fit on Frontier. And so it doesn't matter whether ESnet can carry the data because we can't generate it. Okay. So this is one turbine. You might say, we nailed it. Okay, I already said that. This is a great quote that people tend to pull out with multiscale, and I love it, so I'm going to read it to you. There are slightly different versions on the internet depending on which one you see. We used to think that if we knew 1, we knew 2, because 1 and 1 are 2. We are finding that we must learn a great deal more about and. And this is true in so many senses, and I will skip the philosophical diatribe, but the power of and. There we go. This is 2. And if you had done 1, you might extrapolate that and said every one is doing the same thing. And what you see here is that the upwind turbine has clear air coming in. Oh, sorry about that. I don't know if we dare try to do this again. Okay, let's try one more time. you can hardly see the second turbine there. It's so caught up in the wake of the first turbine. So if you're designing a wind farm and you're thinking about how far apart to space these, you'd better understand what's going to happen. And this is why we do those simulations. Okay, that was and in practice. All right, so where are we now? So coming back to our global scale, we can resolve the turbine scale, the blade scale, up through, let's call it the farm scale or plant scale. And again, in 2023, we're going to do 40 of those. One of the things that we're working on, there are a lot of atmospheric models out there, and it turns out that a lot of them have been around for quite a while. They were not designed to run on exascale computers. We actually happen to be big believers in running on exascale computers. And so we're actually building a new GPU-ready model that will be able to, we can add it to this ExaWind suite, and we'll be able to basically provide the mesoscale input. It's one thing to run one of these in isolation. You can't see a hurricane coming if you're giving it sort of idealized boundary conditions. And so that's a capability that we're developing. Do we really need supercomputers? I think that I've convinced you of that, but that 15 turbine case I just showed you was 11 billion data points. So if you take a snapshot in time, one snapshot, that's 1.4 terabytes. You might argue we don't need ESnet to make a movie, we can just wait for it. But if we're going to be analyzing the data, then we need to be able to get the data. That's just one snapshot. Okay, so why am I here? Why am I here talking to you about this? Because, and this is something that's been said, I just want to echo it from the perspective of a, not exactly in the trenches, but a scientist in the trenches. So the reality of modern science is very different. So I realized that when Inder put up the history slide that I started doing computing when in the days of ESnet 1. It's different. It's really changed. So our projects are multi-institutional. What that means is our people are distributed geographically. We used to compute on the computer that was in our building. You know, it was downstairs. Yes, I carried punch cards to the computer that was in the next building, but it was all local, right? Now the computers are across the country. We compute on Frontier, we compute at Argonne, we compute at NERSC. People like me don't have to worry about where we compute. It's this idea that there are these seamless resources that I want to spend my time thinking about the problem that needs solving and how we're going to solve it, and not about, ooh, I wonder if I can use that computer because I may never see my data. And we run more than one simulation. I've showed you the one that was sort of the state of the art right now, that two, but we are doing multiple simulations. We're always validating, we're always improving. We generate a lot of data. So I grabbed the ESnet map here. So ExaWind is one of many projects in the ECP. I'm on 6 different ECP projects plus several other projects. The red circles are the locations of the people that I collaborate with either daily, weekly, or at most monthly. So I'm one of those many thousand DOE scientists. I collaborate with that many people. Now multiply that by the 10,000 or whatever we are. There's a lot of conversation happening. And I love the science as a conversation. That's absolutely true. So I think I've convinced you, big distributed data, big distributed teams, we are the beneficiaries of what you all do. And now just a thank you to everybody. I want to thank the ExaWind team. There's no way I could put all their names here, but they're a fantastic bunch of people who've done this work. To the folks who run the computers, to the folks who run ESnet, to the folks who fund the work that we do, to ESnet, and to all of you who support the science. And thank you for being here. Now the awkward moments. Sorry, technical difficulties.
Yes.
There we go.
Thank you. Thank you, Anne, for a wonderful talk. Now we're all going to be excited about wind energy, and we're going to look forward to what you recommend, Anne. I would like to introduce the next speaker, Dr. David McCallum. He's a senior scientist in the Energy Geosciences Division at Lawrence Berkeley National Lab and professor of civil and environmental engineering at University of Nevada at Reno. His interests range from high-performance simulations to experimental testing on earthquake simulation shake tables. He started his career in Livermore National Lab, where he developed computational software. And I would like to welcome Dr. David McCallum.
Let's see if the clicker behaves itself a little better with me. So it's great to be here, and I really appreciate the opportunity to represent the entire EQSim team. We are doing large-scale earthquake simulations, as you'll see in a moment, if the clicker works. I think the battery is low on the clicker. There we go. Cover slide. Thanks again. I'm representing the entire EQSim team. This is an integrated team, not only from Lawrence Berkeley National Laboratory, but also Lawrence Livermore National Laboratory. And we have a team, relatively large team of engineers, computer scientists, applied mathematicians, and seismologists. This is truly a multidisciplinary problem. And I would start by noting that rarely, not very often does the venue and the location of the presentation carry such relevance to the topic at hand. And so as I get into this today, I'm here to tell you, you are sitting in the middle of our numerical laboratory. And I'm going to be talking about the Hayward Fault as our case study. Our KPP1 application for the EQSim program actually has a demonstration around the Bay Area and the Hayward Fault. So I'm going to be talking about that. But I wanted to start to talk about in a simple way the crux of our problem and why this is so challenging. But let me start with the building we're in here today. We're near the Hayward Fault. Every person in this building crossed the Hayward Fault this morning. I don't know if you know that. Arguably the most dangerous fault in the country. It runs right underneath Berkeley, runs right underneath Oakland, you know, a very, very heavily populated area, and you crossed it. And so it's really, really an important thing to understand how that particular fault affects infrastructure in the Bay Area. So let's think about the building we're in here for a moment. Suppose we wanted to understand the risk to this building. We could go over to the plant engineering here at LB&L, and we could get the drawings for this building. And those would be detailed, and they would have all the dimensions. So we could construct a computer model of this building and have pretty high confidence in that model because we know everything about this building. Okay, then what do we have to do? We have to understand what future earthquake motions might occur at this site. And that's where things get very, very murky. Faults are under the ground, they're complicated. We have a terribly heterogeneous geology that those waves propagate through to get to the site. And then they interact with the building in a very, very complex way. So our uncertainty climbs tremendously when we have to understand those earthquake motions that this building is going to be subjected to. At the heart of it, the EQSim project is trying to transform the way we develop those earthquake motions and understand how they interact with the structure. And that's really the simple-minded, if you will, thought process to this. Okay, got to go this way. So how have people addressed this problem historically? Well, they've developed entirely empirical models that are based on data. We heard in the last presentation, you know, sparse data. Well, this is a really sparse data problem. And what I'm showing you here is the entire record base of major earthquakes from around the world that is contained at UC Berkeley at the Pacific Earthquake Engineering Research Center. Every single one of those dots represents a measured earthquake record somewhere in the world. If you look at that, the vertical axis is the earthquake magnitude. The horizontal axis is the distance from the site where that earthquake was measured to the fault. And you can see that matrix looks like this. If you look, you immediately see there's a lot of dots on that. There's 21,500 dots. I want you to remember that number as we go through this presentation. That's not enough dots. If you look at the yellow box, which is the region that we care most about, large earthquakes in the near field, that box is almost empty, remarkably. And so we are really talking about an empirical statistical model that is based on a starvation of data to try to develop these statistical models. That lies at the heart of why it's so difficult to predict motions with the current methods at this particular site. In addition, think about the Bay Area. I'm showing you the last set of earthquakes on the Hayward Fault. They occur about once every 150 years. Those that you work here like me happen to know we're 153 years into the next cycle, which is not good. So an earthquake is coming on the Hayward Fault. But if you look at this, the last earthquake was in 1868. That's what was in Berkeley in 1868. And today you can see, and those that you passed the Cal Memorial Stadium, the Hayward Fault goes right through Cal Memorial Stadium. So not only do we have a lack of data where we need it most in the near field, in site-specific regions like Berkeley and the Bay Area, we have no data. We've never measured a large earthquake. There was no seismic strong motion instrumentation in 1868. So that all adds up to a real challenge in terms of understanding the earthquake motions. So what are people thinking about now? And this is really a transformational approach. People are thinking about high performance simulation to model these earthquake processes all the way from the fault rupture, propagating those seismic waves through the earth and interacting those waves with a particular structure to gain understanding. And so that's really the challenge that we're tackling. This is a hard problem. We're talking about modeling hundreds of kilometers in extent. We're talking about massively parallel grids of for example, the San Francisco Bay Area. I'm going to show you that are billions or hundreds of billions of zones, and then modeling that entire process and getting those ground motions. So, this is a hard computational regime to make. But there's light at the end of the tunnel. We are now getting access to these GPU accelerated machines that are extremely fast with very, very large memory. So like the wind project you just heard about, this is a really, really exciting time for us. We are right on the precipice, as I'll show you, of being able to simulate these processes now in reasonable compute times. And so important to this conversation is obviously the GPU accelerated systems that DOE is developing across the Office of Science. Turns out we use multiple of those. We've been using Summit for our really big runs at Oak Ridge, and I'm going to show you an example. We also are using Perlmutter here at LBNL to do all of our infrastructure calculations in a very agile way. And then we're obviously very excited to get on Frontier, we hope very, very soon. The point is we're using all of these in a workflow that exploits each of those, and ESnet is sort of the glue that stitches all this together as we transfer that data from one site to the other, from Oak Ridge to LBNL and back and forth. Oh, goodness. Okay, so here's what our workflow progresses like. We chunk it into 3 components. Component number 1 is the massively parallel simulation of a region in terms of the earthquake propagation. So I'm going to show you an example for the San Francisco Bay Area and the Hayward Fault. We take that data, we transfer that to LBNL, and then we use that in different ways, in agile ways, to look at infrastructure. We may want to look at one particular piece of infrastructure at one location. We may want to understand the variability of response across the entire region. And we also want to be able to go in and inspect that data and look at that data to look at the realism of that data. And when you have 300 billion grid points in your surface of your domain, that's all a very, very big challenge. So let's hold our breath. If they could advance it, it'd be great. I think next slide, please, if you could. I think the battery's dead on this. So what have we been up to over the last 5 years? We have been working on the SW4 code, seismic wave propagation, 4th order in space and time, to really optimize it for this particular problem and to optimize it for GPU-based platforms. So I won't go into a lot of detail, but we are looking at very, very carefully adaptively grading our mesh so that they're matched to the geologic material properties in a vertical direction. We have pencil domains that we then propagate across the nodes on the massively parallel system. So a lot of work has gone into that. Next slide. They're having trouble as well. Yeah. So this is an example. When you're at the mall, you see the map of the mall, you are here. This is a very, very large simulation of a magnitude 7 earthquake on the Hayward Fault. In this case, the hypocenter is the star, and those seismic waves are propagating north. That's what you feel when you feel the earthquake, are those waves going underneath your feet and shaking the ground. This is a very, very large model, and it has unprecedented frequency resolution. We're resolving 10 hertz motions, very, very high frequency motions that are important to resolve for understanding the response of infrastructure. And we have about 391 billion grid points, and this was run on about 3,600 nodes of Summit. So this was a execution that we ran last fall, and we're really, for the first time, being able to resolve these ground motions at frequencies that are relevant to engineered systems. A building like this may have a natural frequency of maybe this short building of 1 to 3 to 5 hertz. We have to resolve ground motions up to 5 and 10 hertz in order to be able to actually have motions that are relevant to the response of that building. Next slide. So to give you an example of our progress, what I'm showing you here on these GPU accelerated platforms is the entire history of earthquake simulations of ground motions in the San Francisco Bay Area, going back to the year 2000. And what you see each of those colored dots is a different research group that modeled the San Francisco Bay Area. And I'm showing you the progress with EQSim in the turquoise dots on the right. Once we get on the accelerated platforms, we did the algorithm development to optimize the SW4 code. We got it running on Summit, and you can see the tremendous progress that has been made as a result of being able to utilize these new platforms. Next slide. So the other thing that we have to do is we have to, and this is where ESnet really comes in and is important, we have to be able to couple the motions from that geophysics model into our local soil structure models in a rational way, in a way that preserves the complexity of those incident and climb body waves and surface waves, so we get those effects. So we have developed and implemented a domain reduction method within our framework that allows us to go into that large database that we get from the Summit or Frontier simulation to plop our structure and soil island down wherever we want and efficiently generate the boundary motions on that local model so that we can do a substructure analysis. And this is an example of that. Next slide. So what does this translate into is our ultimate workflow, where we have our geophysics simulation on the top, and that's something we'll do at Summit and Frontier and have been doing, billions of zones, hundreds of billions of zones, 200,000 time steps, very, very large data set, as we'll see, using ESnet to translate that data over to Berkeley Lab. And then we have the flexibility, once that data set is here, the near surface data set, of doing all different manner of infrastructure simulations at will and very agile. And so ESnet is really the enabler to getting that big data set here efficiently and allowing us to operate on that in order to look at the risk in the system. Next slide. So we stitch all that together and we get to something that looks like this. I'm going to show you that earthquake again. The red dot is a location where we want to analyze this representative 40-story steel moment frame building. And you can see the seismic waves arriving at that site. And that building is now responding to that. And you're seeing the damage evolution in that building as that building yields that steel frame building. If you look at that boundary, it's working really hard, isn't it? In that substructure model that we've run here at LBNL, it's working really hard because those complex incident seismic waves are very, very complicated. They're arriving at that site, and we're representing and honoring the complexity of those waves in that analysis. Next slide. So effective data management is critical. These data sets are very large, as I'll show you in a moment. So we take our geophysics model, we use the EQSim ECP developments for data. We create HDF5 data containers. We compress that data with ZFP, which is a compression algorithm, and then we translate that data either in terms of just surface motions or a near surface volume of motions that we can use in a number of ways. Next slide. So if we look at the fact that we don't know which way the Hayward fault is necessarily going to rupture ahead of time, I showed you a south to north rupture. That would be bad for Berkeley because it's directing all that energy towards Berkeley, but it could rupture north to south. So we have to look at that full suite of equally probable rupture scenarios. So that means we have to run maybe 10 or 20 different rupture scenarios of the Hayward fault to fully characterize the risk that is involved. So that generates something on the order of 3.2 petabytes of data just for the surface motions. As we move on and start to generate the volume motions, that number is going to grow. But we need to move those kinds of data very efficiently. I mentioned to you the size of the observed database when we started. That's shown in green. That's 21,540 time histories from around the world. When we do this simulation on Summit, we get 3.14 billion time histories throughout that entire domain at every 2 meters. So we have ground motions everywhere and can look at the relative motions as well as how those motions interact with the structure. So that's sort of the data challenge for us. Next slide. So we are an advocate and a user of ESnet. It really is key and enables our workflow. So on the left, we have our summit simulations, for example. We start with 200 terabytes of data. We compress that maybe by a factor of 50 to 100 for our structural evaluations. We chunk that into 2 gigabyte segments, and we transfer that over to Perlmutter to actually do our structural simulations. Next slide. So good for ESnet. This is really great. So if we think of the data we transfer from that grid that's 120 kilometers by 80 kilometers at 2 kilometer, essentially 2 meter spacing, that results in about 3.14 billion grid points that we have to transmit data for. Every one of those grid points has a earthquake time history, a velocity time history, 2 in the horizontal direction and 1 in the vertical direction. So you do that multiplication, it's 9.42 billion grid points in that data set that we have to, time histories that we have to transfer. And so we've been testing this particular run on ESnet. We can do that in about 9 to 20 minutes, depending on our compression ratio, which is remarkable for us. Next slide. So what does this get us to? This capability, end-to-end capability, for the first time is allowing us to look at the complexity of the risk to structure in an entire region like the San Francisco Bay Area. What you're seeing here is the damage potential, where red being the hot colors and more damage, for a representative 20-story steel moment frame building at every location in that Bay Area. You see that that's very, very complicated. That doesn't look homogeneous. The complexity of the fault rupture, the complexity of the geologic path that modifies those waves, and then the complexity of the interaction between those incident seismic waves and the structure lead to a very, very complicated damage pattern. And this is exactly the kind of things that we're trying to get out of ESnet. Next slide, and EQSim. So our end game is to be able to run many realizations of a Hayward fault rupture, not one, but 10 or 20 or maybe even 30, so that we can fully characterize the potential risk at a given site anywhere in the San Francisco Bay Area. So that is really the end game of stitching all these things together. Next slide. So we are also trying a real-time example. So let's click on that URL. Hopefully it works better than the clicker. So when I started this presentation, we started the transition of those 9.42 billion time histories from Oak Ridge to here, and they're done. It took about 7 minutes and 35 seconds. The effective speed was 7.73 gigabytes per second. So go ESnet. So with that, I will end, and sorry about all the IT issues.
Thank you, everyone. Okay, Dave, that's your last slide. Yeah, okay, it was a big team that's working on the simulations, and thank you so much, everyone, for joining us for unveiling ESnet6. You've heard from our funders, our program managers, from what we accomplished, from our wonders that have helped us accomplish this, and from the scientists on how they plan to use this network to do great science and for benefit of society that'll help all of us. So thank you for joining us today. I know many of you have traveled from long distances to be here, taken time out of your day. Really, really appreciate the support for ESnet that you have shown, and we hope to continue to live up to your expectations. So thank you.